Ladies and gentlemen, so my name is Maciej Szabatowski. I'm going to be a host until, let me say, lunch break, then Remigiusz will take over. I have a big pleasure, I will repeat it once again, to be here. I will try to stay calm. I will try to be as supportive as I can for our speakers, and I will do my best to be a nice breaker for you in between. First of all, a couple of facts for you and the house rules for today. People will be coming in, coming out, going out, no problem. First of all, this is a conference. You can easily switch between the 3 rooms that we have for you today. First of all, I would like to kindly request that you put your phones in a silent mode. It will be a token of, let's say, gratitude and appreciation for the speakers as well. So if we can spend a couple of seconds doing it right now, no problem, please do it. Let's try also not to interrupt our speakers during their speeches. There will be a very brief but hopefully exhaustive Q&A session at the very end of each of those presentations. And well, it's important to say it, and especially to our speakers, to our viewers online, that first of all, we welcome you also right here. So wherever you are, in whatever time zone you are, the questions will be only asked right here. So we are doing, let's say, the old school stuff right here. And my t-shirt, which is on me today, is also a kind of a symbol for the old school that is going to happen right here. If you go to room number 8 and you are happy enough to be joining us here live in Wrocław, you can jump back into the 90s. I will not spill the beans. I will not give you the details. Please believe me, I was there and I was totally gobsmacked to see all those facts and all those, let's say, beautiful games that are prepared there. Nothing more from me. Just check on it during the break. Speaking of the devil, the break. So the lunch break will happen between 1:25, so 13:25 and 14:10 p.m. So eating is possible within the walking distance. We are actually at the very city center. So wherever you go to all around, you should be able, excluding inflation facts, but please forgive, it's all around the world, just to grab something nice to eat. Coffee and snacks available throughout the whole conference right here at the venue. You should be aware that there are at least 3 places where the coffee is available. I think this fueling up is really important to all of us. So this is the 9th edition of this Code Dive conference, led by Nokian people, by people who really spent a lot of time preparing all this. So maybe at the very beginning, I would once again ask you to give a warm applause for them, just to prepare everything that is happening today. Thank you so much. Okay, the last words from me. Welcome active programmers, welcome programming enthusiasts, welcome idea-sharing ready people, welcome everyone who is ready to listen today, to grasp some more facts, to exchange ideas, to be seated right here and maybe socialize a bit even afterwards, because in the evening there is going to be a nice party, especially for the speakers right here at Kontynuacja Pub. So if you feel that it's not enough, just jump in right there. I'm sure that there will be the rest and you will be ready to fuel yourself up a bit more. Okay, so I think I really went through with the main facts. Remember, room number 1 is the main one, room number 7 and room number 9 are the ones that are devoted to the topics that will be presented here, and room number 8 is the place where you can check this entertainment part which was prepared by the organizers. Let me check only if we still have anything to be passed on. Oh yes, this is about the contests. So contests ongoing, you can get a Nintendo from Nokia recruitment stand, or plenty of interesting books from PWN, the Polish publishers, and Helion publishing houses, of course in English. I hope so, at least. And remember about this coffee, it's on the 2nd floor in the bar, from the food truck on the ground floor, and from the ground floor bistro. So I think that will be it from me. Thank you so much for being patient with me. Right now I would like to pass the microphone on to the first speaker, but first a couple of facts only about the person. So maybe the very first fact is that he got up at 4:30 in the morning, which actually is a big challenge. I would never be able to do that. So I think he deserves even more respect and proper welcoming in the moment. So Borislav Stanimirov, he has been writing C++ software for more than 20 years. Really? Looking at his face, no. The majority of his career has been in video games, and in the past 4 years, he's been working on software for medical devices. He has worked on C++ software for all kinds of platforms, desktops, mobile devices, servers, and embedded. I think he will tell you a bit more, and he will sign his own name by presenting the topic today. We have it just in front of you. Thank you so much. Borislav, please jump in. Please give a warm applause to the first speaker.
Thank you. Thank you. So, hi, yeah, I'm Borislav. If you want to follow these slides on your laptops, mobile phones, you can find them here. That's is.gd/beyondvec. You've already heard a couple of words about me. I do also a lot of open source stuff. You can find my GitHub profile and find my things, like them, give them thumbs up, stars, and whatnot. I work at Uray. That's we cure cancer with hardware and software, and there's a short technical overview on my blog if you're interested of how we do it. So, about this talk, it's about vector, but it's also about alternatives to standard library types, and they have a lot of history in teams, in companies, and in projects. Ever since the first standard library for C++ was developed, there were people saying, no, that's not how you do it. And that alternatives of standard library types are especially popular in multi-platform software and game development. Basically what I've been doing my entire life. Why, though? First of all, it might be the feature set. So that's probably the most popular reason. For example, string view came in C++ 17, span arrived in C++ 20, but these are not really hard to implement concepts even with C++ 11, and to an extent, especially for span, it's been a popular thing, mostly called memory view, even before C++ 11. So those can be called standard library alternatives because the actual standard library types are not yet available. Many people say, and I join them, in saying that map where the key is string or set of strings, stood set of strings, are practically useless before C++ 14 and transparent lookups. And the same thing can be said of an ordered map and set where, again, the key string or the set of strings before C++ 20. And so people have developed alternatives which allow transparent lookup before C++, before they actually came to the standard. And of course, C++ has been called the language of bad defaults. And that's especially getting more and more popular of a saying these days with the popularity of Rust. But even before Rust came to be, there were a lot of people saying that the defaults in C++ in terms of moving constants and then a huge amount of things are just not good. The defaults should be different. And for example, Rust has different defaults. So there have been types developed with different defaults in mind. And of course, there's a lot more examples. And basically, the idea of experimenting with the standard library types and creating new standard library types, this idea was the thing that made Boost, the Boost library collection. I'm sure you've all heard of it. Anyone here not heard of Boost? No hands are up. OK, so another thing may be performance. So certain types in the standard library are not very well optimal, and IOStream is maybe the worst offender here. Even naive reimplementations of IOStream usually are better performant than IOStream itself. So of course, maps and sets are trees, so they are dispersed in memory usually, and people who often have to traverse maps or sets have created flat maps or sets, which keep the data in a contiguous block of memory. So that's something that will allow you better performance, right? stdhash is not the best hash implementation out there, but at least that's a document extension where you can easily replace stdhash without actually having to re-implement the standard library for it. And of course, many more examples here. But an especially popular offender in performance are allocations. So a lot of reimplementations of the standard library have been done because people wanted to deal with allocations differently. And allocations are bad for performance, of course, and I will get back to that, but let's just assume that they are for now. And yeah, as I said, maps, sets, and lists, they keep their elements dispersed into memory. In different, every element is a separate allocation. So this is somewhat understandable because they are trees or lists. But people do like node pools and let's say list with a node pool, which minimizes allocations, or a tree with a node pool and stuff like that. So unordered map and set are actually very bad in this regard because they do allocate a node for every element that you insert inside. So hash map implementations which keep a contiguous block of memory for the elements didn't have existed for many, many years. Another example is that, so you can deal with most of these things, even with the standard library types, if you use allocators. But for example, stud function does not have an allocator. It used to have one, but it got deprecated and removed. So currently, you cannot use a custom allocator for stud function. You're forced to use the default memory allocator, so new delete, when you create functions that actually surpass the small function optimization. And of course, many more examples here. And yeah, I said allocators, and allocators are notoriously hard to use and especially easy to misuse. You can easily, trying to improve performance by introducing a custom allocator, it's relatively easy to actually degrade performance with your poorly implemented custom allocator. Another reason for re-implementing standard library types would be predictability. And that's, but the performance reason would be more popular for game development, for example. That will be the driving force for re-implementations in game development. Whereas in multi-platform development, if you do want a re-implementation, that's usually because you want predictability. Predictability between platforms. So C++ has also been called the land of implementation defined. There's a lot of implementation defined stuff in standard libraries. For example, the size of pretty much every standard library type, say for a couple of exceptions, is not defined. And you cannot rely on the size of these types. The size of small string. Currently, in all popular implementations, the small string optimization gives you a default capacity of 15. But for example, not so long ago, libc++ used to have didn't have a small string, but had like some kind of a copy on write optimization for strings, which was terrible and different. And then people were usually replacing, when people using stud C++ were replacing the string from the get-go because of this. Iterators are who knows what. So they can be pointers, and the specification for iterator does not contradict you using a raw pointer for it. But they're never this. They're some kind of structs. Their size is different. For example, they vary between debug and release, because if you want to debug iterators, you will need to have a reference to the container in the iterator and stuff like that. So you cannot rely on the size or even the type of iterators. And there are many more examples. For example, to get the const char star, well, this call right here, so cster from path, would not return a const char star. You would think so, but for example, on Microsoft STL, it returns wchar_t. And maybe you don't want that in your multi-platform code. And again, many more examples here. And another thing that people often cry about is compliance. So compliance, by that I mean things that is defined by the standard, but people just don't like for some reason. A size would be a 64-bit unsigned type, according to the standard, on a 64-bit compiler at least. But some people don't want that. They say, I will never have more than 2 billion elements, so I'll have it a signed 32-bit type and get some performance out of this, because I don't have to deal with integer overflow, for example. And this is, again, popular in game development. the very popular offender here, and especially now with the popularity of Rust, is stud move if no except. That's like the great divider in many C++ arguments, I guess, and fights, physical fights even, why not? Typically, a vector, say, or a container that keeps a contiguous block of memory for elements, will try will copy elements if their move constructors are not no except move. So if they're not, it's not necessarily trivially movable, but say Rust people will say that everything should be trivially movable. I don't quite agree with that, but I personally agree that every move constructor should be no except. Anyway, stud function must be copyable according to the standard. So you cannot capture, say, a unique pointer is stud function. So people have implemented unique functions which are not copyable. And stud function of it's with the move if no except. I have a story here. So stud function did not have a no except move constructor according to the standard. So standard people thought that if you want to have the small function optimization, the small function optimization is this. Basically, you keep a buffer of memory with your function. If you capture something small, you don't allocate. So you can write it in this buffer for small captures. But the thing is that if you move such a function, which is not allocated, but keeps its captures in this small buffer, and the move constructor throws, that means that the move constructor of the stud function will also throw. So standard people said, OK, so we will not require stud function's move constructor to be no except. But that was a silly thing to say, because you can make it no except if the underlying object is no except move constructible. So you can use the no except operator for this. Anyway, they fixed this, but I had a very, very nasty problem with something that was copied in vectors because it just had a stud function inside of it. Terrible, terrible. And it was impossible to detect until I accidentally stepped in some code. I really accidentally stepped in some copying code. I was like, what? What's going on here? And again, stud map, its constructor, its default constructor is not no except. So that's thanks to Microsoft, basically. Thank you, Microsoft. But that's pretty much the only bad thing I have to say about their standard library implementation. But if you keep maps in your object, they will be implicitly not no except move default constructible. And many more examples here. So that's why people do reimplementations of standard library types. Basically, these are the reasons, and I didn't list all examples, but these are the overarching reasons. And don't do this. The standard library is great. There's a lot of effort invested in making sure that it works, it does its job reasonably well, and it will minimize the opportunities for you to shoot yourself in the foot. But at times, you are smarter than that. I know you are. And you know that you can reimplement something for your particular use case. So when you do, please, if you reimplement something that resembles standard library type or a standard library type in a code base, typically this thing will propagate inside all or a significant part of this code base. And even a small bug can have, or a small performance degradation can have a huge impact over the entire software. So you need to test stuff rigorously. You need to use sanitizers. You need to benchmark that your goals are achieved, and basically be very, 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 I have 26 more minutes. Very, 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 very careful. And this talk is about stdvector. But stdvector is just a placeholder here, right? I will give you some examples of stdvector reimplementations and the reasons behind them. But I think that my idea here is that you should explore stuff. If you are convinced that standard library is always the best solution ever, you should try to explore alternatives and try to understand why they came to be. So I will cover some use cases, as I said. I'll give some examples and some demos. So first of all, what is stdvector? It's a container, right? So it holds a contiguous block of memory inside of it. It allocates this memory. It owns this memory, so it deallocates it. So to be precise, it's the allocator which allocates and deallocates, but the vector tells it when and what to allocate and deallocate. It owns the objects. It's a mutable container. You can add or remove objects. And it's a container of mutable objects, so you can change the objects without modifying the container itself, so without resizing the container in any way. And it has a bunch of implementation-defined stuff inside of it. For example, the size of stdvector is not defined by the standard. And then a lot of other stuff too. And you might say that all of these requirements are trivial to challenge. You don't want contiguous memory? Don't use stdvector. Use deck, list, whatever. You don't want to own the memory or the objects? Use a reference, vector reference. That works, right? We've all written vector references, right? If you don't want to own the objects, use a reference wrapper, or just a vector of pointers, right? It works. If you don't want your container to be mutable, use a const vector, right? It works. And if we agree with that, we come to our first vector alternative, which is myvector. And this vector alternative is the exact same thing as stdvector, as defined by the standard, with all its tidbits, with all its specifics, and with all its implementation-defined stuff. So, seemingly, absolutely pointless, right? But it does help. It helps with predictability. The vector, the stdvector's growth factor, is not defined by the standard. So if you keep pushing elements, for example, the vector's capacity is 10, and you push one more element to make it to the 11th element, how much will the memory grow? In some implementations, it will be twice. In most implementations, so we will reallocate 20 more memory for 20 more objects. In other implementations, it will be like 3 seconds, so for 15 more objects. It depends. But for some code, this is actually very crucial. You want to have, if not a control, then at least a clarity about what's happening over there. The iterators, as I said, iterators are God knows what. Structs which may or may not have reference to the vector itself. You can define your iterators to be precisely this. And vector is actually not the very typical example of a container from which you will have iterators just flying around. You will typically have indices. But if you were dealing with list, for example, and list has a very, very narrow use case, but it's still not zero. So if you're dealing with std_list, you will typically have like a bunch of iterators flying around. Also, shrink to fit is not required to shrink the vector. You may want it to shrink the vector. Also, there is a feature set. I started with the feature sets, things that have been introduced in the standard, but you may not necessarily have this standard available. That, for example, in place, didn't used to return a reference until C++17. The move constructor of vector wasn't no except until C++17, and a lot of other examples. No, not a lot, but a couple of more examples, I guess. And there's, again, move if no except, compliance. It's really easy to do huge amounts of copying if you forget to make a move constructor no except. Or if you rely on compiler-generated move constructors and you just add unknowingly stud function, for example, 2 years ago, or a compiler or standard library from 2 years ago, and you add a stud function in one of your types, and suddenly, without you even noticing, they all stop being no except move constructible, and the vector starts copying stuff. And also debug performance, and that's again very typical for games. Debug performance should not be underestimated. Vectors, typically the standard library implementations, have some kind of checks. That's especially true for Microsoft standard library. I've personally been, by introducing a custom implementation of vector, I was able to improve like twofold, so 100% improvement of the debug performance of the software. And no improvement of the release, but it made lives of programmers so much easier. And that I keep saying std move if no except. What's this? So if you insert an element in a vector, and it's not the back of the vector, but say it's the front or somewhere in between, the rest of the elements that are displaced, need to be moved to their new slots. If you need to reallocate the memory for a vector, if you push past its capacity, the elements from the old vector need to be moved from the old memory, need to be moved to the newly allocated memory. If one of those move constructors throws, it's actually really hard, well, not impossible, I'd say, but in certain cases it is impossible. In most cases, it's really hard to guarantee that the coherency of the container is preserved if you catch the exception and then go on with your life. A naive implementation of vector, if a move constructor throws, if you just move objects, and one of these throws, you will end up with a piece of the vector in the old memory and a piece of the vector in the new memory, for example, and that's terrible. You will have to take care of this. And a lot of implementators of standard libraries, even in the cases where they could take care of this, have not done it. And here I'm saying that only Microsoft standard libraries implementation has actually gone all the way and done all the things possible to preserve your coherency and try to use your move constructors even if they're not no except. And I have a demo here. So, can everyone see? I assume that's a yes. This is a very simple type which only logs its copies and moves. That's basically it. So I have a vector of these people here, and I add Alice. So and then I log pushing Bob to front. Here you see that that's the log over here. And Bob is expectedly move constructed inside, but because this had to reallocate a new block and move the old contents of the vector, i.e. Alice, in the new memory block, Alice was copy constructed in the new memory block. Only because I failed to make my move constructor not no except. If I make it, if I make it no except, you see, Alice gets move constructed. And that's GCC. So if and the same thing will happen in Clang. But if I use Microsoft's standard library, you see that both are move constructed, but I do have this no except constructor here. Let me just comment it out. Okay, let's make sure that it worked. Okay, both are move constructed. So the Microsoft standard library has gone out of its way to try to preserve your vector coherency in case of throws as much as possible. And there are cases where it will also copy the impossible cases. But anyway, this is again the language of bad defaults. The default should be that the move constructor is no except every time, but it's not, as you can see. Anyway, oops, I pressed fun for some reason and not control. So can I do this? Apologies, unfamiliar with this laptop. If I was on a Hvalibog, it would have been a breeze. Yeah, and then for speaking of, this slide is kind of ahead of myself, sorry. So Microsoft STL is so good that it even deals with certain standard compliant implementations that developers of other standard libraries have deemed impossible. If you have a vector of non-copyable objects and you try to insert elements at the front or in the middle and not at the back, it will fail to compile on standard libraries other than Microsoft STL. And if you try to log your copies, you will see that if you insert an object in a vector and it leads to a reallocation of memory, it will copy objects. And implementers of libc++ and libc2c++ say this is impossible. Well, it's not impossible, but it's really hard to implement. You have to invest a lot of your time in order to make this work. Again, this is all because of the fact that if a copy constructor in this case throws, or a move constructor throws, you will lose your vector coherency very easily. So the implementation has to push an element to the back and then rotate other elements by moving in order to place it in the correct spot in order to preserve your coherency. So, and yeah, this is an example of immutable objects, right? So non-copyable objects in a vector. And speaking of this, this leads me basically into another reimplementation of vector. What do I mean by immutable? It's not const. So a const object, it is immutable, but it's a very poor representation of an immutable object. An immutable object would be something like string view. You don't change the object itself, but if you need a change, if you need to make a change on the data represented by this object, you make a copy. You make a copy on write, basically. That's the idea behind immutable objects. A cow, copy on write. If we want to make a vector immutable, this is something naive we can do. We can say we're implementing the erase function. We can create a copy of the vector. We can erase the element that we want erased and then return this copy of the vector. So we copy the vector on write. The original vector remains the same, unchanged, and we get a new copy of this vector with this element removed. But this is very naive, right? We copied the erased element itself. So we did a pointless copy of something that we're going to erase anyway. And we allocated more memory. We allocated, for the copy, we allocated more memory than we actually need because we allocated memory for the erased element as well. This is a better implementation. You can reserve the required size, and then you can move the first part of the vector, and then you can move the second part of the vector inside without the erased element. And that's a library, immer, which deals with immutable objects. It's great, it's awesome, and I'm quite into immutable objects these days. So if you want to talk about immutable objects, come and find me. Immutable objects are great. Anyway, most vector alternatives, however, are there to deal with allocations. So as I said, a couple of more words about allocations. Allocations are really slow. Making an allocation with new or delete or malloc needs to do a lot of stuff. In many cases, this will lead to a syscall, which is extremely slow. It won't necessarily always lead to a syscall, but in syscall will deal with physical memory pages, but even not syscall will deal with some kind of paging of memory. And this is the obvious cost, right? So you're basically calling new or malloc. It will have to find a free chunk, depending on what kind of allocator type is. It will have to sync this thing, so basically some kind of locking is involved, I guess, or a free list, which is also not great for performance. But there's this thing called commit size, which will reduce the amounts of syscalls you make. Anyway, too much details, I guess. And there's the not so obvious cost of allocations, which is that if you make an allocation, the memory, if it comes from the operating system, will need to be cleared, in case there are passwords or private data inside left by some other process. And there's also fragmentation. If you allocate small chunks of memory of different sizes, you might find yourself in a state where you have a gigabyte of memory, but in contiguous chunks of, say, 10 bytes, and you cannot allocate anything more than 10 bytes. That's a terrible fragmentation problem. So the rule of thumb in this case is basically always avoid allocations. If you have two mostly equivalent pieces of code and one makes an allocation, the other doesn't, always prefer the one that doesn't make an allocation. That's a great rule of thumb, and we do have exceptions for this, but you really have to know what you're doing in order to follow an exception here. So there are custom allocators, of course, and as I said, they're hard to use and easy to misuse, and stdpmr helps a lot in this case, but I say not much in the slides. It does help a lot, but it's not a lifesaver. You still need to manage even your polymorphic, not your polymorphic allocators, but at least your polymorphic memory resources. And in case you want your allocators propagated, and that's not true for PMR only, but for all kinds of allocators, you need to manage the propagation of these allocators as well. which is not really easy, and very easy to create a bug in this case. A bug that you will not notice for a lot of time. Your code will run with this bug for a lot of time without you actually noticing it. And stdpmr, of course, is not zero cost, and by that I don't mean that it's not zero cost in terms of performance. It's almost zero cost. It's a polymorphic memory resource, so every allocation leads to a virtual call, but the performance degradation because of the virtual dispatch is negligible compared to the allocation itself, usually. There exist allocations which are pretty fast. But integrating PMR in your code base is not zero cost. It usually involves a lot of changes and tweaks and modifications. It rarely works like you replace this part of the code here and then you're done. This part of the code is optimized. The work is being done to improve this, but it's very, very far into the future. It's a language change, so C++26 here, it's a very optimistic projection for when improvements of allocators will be in C++. So we're set, right? As I said, I'm not strictly against PMR. In fact, if you replace every container in your code base with a PMR container, it will very likely be beneficial in the long run. It won't be beneficial on the second after you do it. It will probably lead to no change whatsoever, but it will allow you to make changes and optimizations in the future. So PMR is great. Do use PMR. Anyway, in some cases, you can completely avoid allocations, right? What if we know that the size of the container, of the vector, is always smaller than a given n? And some people might say here, well, stdarray. That's what it's for, right? But is it? So stdarray is basically when the size always equals n, not when it's always smaller than n. Because okay, so the size is fixed, right? And then you might say, but what if we use a helper integer next to this stdarray, telling us how much elements inside we actually need? We still have to construct all of them, right? Okay, you might say, but what if they're posted array of ints, or something that we don't care about that doesn't have any constructor, so trivially constructible? Well, we still have to copy all the elements if we copy an array, right? And this is a small demo here too. So I have my logging type, and I have an array of 5 elements here. So these are 5 default constructors over here. Then I set the first 2 elements to Alice and Bob, and I copy this array. And of course, I copy Alice, I copy Bob, but I also pay the price for copying the rest of the elements of the array. So just having a plain helper size is not worth it, basically, in this case. And that's why people have invented static vectors. Static vector is basically a vector with a fixed capacity. So it keeps its buffer, much like stdarray, inside. But, and so the implementation of static vector include boost static vector, which is a great, thorough implementation which does everything by the book. And I have this implementation of mine, which is terrible and does 90% of the work with 10% of the code, but it's much faster to compile and much faster to integrate because it's a single file. You don't need like 80% of boost in order to put it in your code base. For example, it does not care about about no except move constructors, I should say. It does not use move if no except. It always moves. So if your move constructors do end up throwing in my static vector implementation, it will end up in a very, very terrible state. And it does not have exceptions for add functions. But this is very rarely I meet people who rely on exceptions, the exceptions of add functions of vector. Anyway, but it has no allocations at all. And we only copy what we need. Here's a small demo. It's basically the exact same code, but so we create a vector, no default constructors happen. We create 2 elements. The constructors are not logged here, but then we copy the vector, and only 2 elements are copied because the vector, even though it has a capacity of 5, moves to objects. So that's expected, right? That's very, very trivial. But can we have the best of all worlds? On a couple of occasions, I mentioned small something optimization, small string optimization, small vector, small function optimization. So can we have a small vector optimization? And yes, we can. We can have a vector which includes a buffer which is only used if the elements does not exceed this capacity. And again, there's boost small vector for this, which is a thorough by-the-book implementation. There's my implementation, which does 90% of the work with 10% of the code. It does not care about no except move constructors, no exceptions net, and it's a single file. And this is like the use case for this will be vectors which are smaller than a given size at the vast majority of the time. And in such cases, you will get cache locality. So all the memory will be in the indexing elements of the vector will typically lead to cache hits, even because it will be, for example, a local stack variable with its buffer, or if you have a vector of these vectors. And there will be no allocations in these cases. I find it very useful in cases where I have an object which can contain either one or many of something. So I guess the popular implementation of this will be some kind of a variant of vector or object. But the easy implementation will be a small vector with a default capacity of 1. So if you have one object, you will have no allocations. It will be cache local. And if you have many objects, it will be allocated and moved to some kind of memory. But your usage will be the same. Your performance will be better if you have one element. So I have a small demo of this too. Again, I have 3 elements in a vector of capacity 3. No copying or no moving of elements has happened yet. And if I add one more element, move constructed the previous 3 elements into the newly allocated dynamic block. So what if the size is absolutely random, you might say? Okay, can we use stdvector now? Please, can we? Maybe, but I have a small detour to make. What if we have a block of memory? So imagine this is our memory, and the red parts are something that's allocated by another part of our software, and we don't have access to it. And we allocate 3 bytes. Okay, this will happen. These bytes will be allocated for us. If we use realloc, who here is familiar with realloc? A lot of hands. Okay, so if we use realloc, in this case, there might be an opportunity to grow the memory without actually reallocating. So it will be pretty fast. It will just increment a pointer, right? The best kind of allocation. But if we want to realloc yet more memory, the old memory will be mem-copied in the new location, and then the new size will be allocated for us. And there's this thing which is Windows only. So if you have a block of memory on Windows, we can use expand. Who here is familiar with expand? Almost no hands. So here's how expand works. You can allocate some memory. It will allocate 3 bytes. You can expand it to 6. It will happily do so. But if you want to expand it to more than it's actually available, it will return null. It will not mem-copy the memory from under our feet. So memcopy, as you know, disregards constructors and destructors. So it's not so realloc is not applicable for stdvector. Expand, however, is. But it's not a standard function, even though it can be. Because if you can implement realloc in some kind of sensible way, there is literally no way you cannot also implement expand. But crucially, there is no expand on POSIX, only on Windows. Anyway, I'm very angry about that. So it's very sad that expanding is not popular, but luckily most custom allocators do offer an expand function. And expand can work with vectors. But what if you want the benefits of realloc, but you cannot use expand? Oh yeah, C++23 has allocated list. It kind of helps, but it doesn't really, because it's a one-shot call. It only returns either more or exactly as much memory as we requested. So if we don't care about constructors and destructors, if you have trivial types, pod types, int, char, struct of trivial types, you can use a PodVector. So a PodVector is something that makes use of realloc, memcopy, memmove in order to optimize your memory usage. I have an implementation of my own. You can see it here, PodVector. But there are very likely many other implementations. Crucially, there is not one in Boost, though. Or at least I'm not aware of Boost having a PodVector implementation. Also, my implementation uses expand if available. So you can provide an allocator with expand, and it will happily work with it. And it allows a recast. I will save the demo because it's not so interesting. Anyway, you can basically mix and match these kinds of vectors in different types. And the last thing I want to say is that right now, your code base, after making use of my talk, has like a bajillion vector types. Small vector, pod vector, stud vector, PMR vector, whatnot. How can you call an algorithm on these vectors? Now, const reference wouldn't work. Templates will work, but templates are always in the header. They will have to be recompiled every time. Your compilation time will suffer, and your code will have to be open source in these cases. So, well, if we use this, it's a contiguous block of memory, right? We can provide a pointer and a size, and that's the exact same thing that we want to achieve, and this is called studspan. And that's why I said studspan has been around since C++, since C times even. It's basically a pointer and a size, or a begin and an end, the same thing. The trivial idea, it has been around for many, many years, and it doesn't necessarily need C++20. It doesn't necessarily need C++ even. It can work in C. And there are a couple of span implementations for you. There's boostspan, there's myspan. Of course, I keep promoting my library. I'm so great. And C++20 has studspan, which is there, the exact same thing. And here, there are no magic differences and whatnot. So thank you. Thank you very much.
Thank you so much.
One. Big applause for Borislav Stanimirov for his first speech today. Please, let's warm up as well. Please, let's do it once again. Thank you. So, this is not the end. We promised ourselves that we are going to set the rules for ourselves, and at least 2 questions, brief ones, can be asked from the room. So if you're watching us right there online, please stay tuned with us as well. So 2 questions will go around the room. Please raise your hand if you would like to ask any questions to our first lecturer, our first speaker. Borislav is waiting for your questions, so hopefully there will be some inside the room. Let's have a look around. Oh, there's one person, so I'm just passing the microphone on.
One, two. Okay, my question will be about the PodVector implementation in your library. It seems like you've ignored the fact that compiler is actually pretty smart about optimizing things. And in the case of, how was it called? When an object doesn't need a constructor to be constructed, the compiler can actually optimize things to actually use the memcopy.
That's true. And in release, when you compile with optimization, where the optimizations, a vector of int and a pod vector of int will have absolutely no difference in performance, unless you do a lot of allocations. So ideally, a pod vector will give you a benefit by using realloc for allocations, as opposed to vector, which will have to realloc its growth buffer every time. But if you don't do a lot of allocations, they will likely have the same performance. Again, they will also likely have the same performance in debug. But vector actually does call a lot of functions inside. And if you compile with no optimizations, these functions will be called. Now, these won't be constructors and destructors in the case of int, but it does call a lot of functions which are expected to be optimized by the optimizer, optimize the way, basically, to copy, to construct. Most vector implementations don't use placement new. They will call allocator construct. So allocator construct for integer without optimizations is still a function. It's a noob function, right? But it's still a function, and without optimizations, it will still lead to a call. And that's why I mentioned debug performance. And usually debug performance is improved significantly with PodVector compared to stdvector. And since PodVector's iterators are pointers, basically row pointers, it has the best possible, say, iteration speed even in debug. And if you use iterators with stdvector, even with int, of char, of whatever, it will be orders of magnitude slower because of the implicit function calls, which are not optimized the way typically in these cases. So yeah, when you optimizations are on, there's literally no difference besides moving things around.
Okay, that would make sense for me. Thank you.
And maybe one more question anywhere from the room. Someone was the first one to go. Sorry.
Hi.
Hi.
About the Microsoft Visual Compiler and the moving constructor. Am I heard? Yes.
Yep.
You said that Microsoft compiler is trying to.
Not the compiler, the standard library, but yeah, go on.
Yeah, the standard library included in this compiler, yes, of course. It's trying to make the containers coherent in case of exception during
During moving stuff.
Yes.
Right.
To what extent can it go?
Actually, to a great extent, they have these. Now, if an exception in your move constructors does happen, it will lead to a terribly slow code, which they called a rollback, which is only compiled in if you have a vector of no except false movable objects. But they have this kind of a rollback mechanism, which basically starts to reinsert pointers in the vector, objects in the vector, and preserves both buffers so they can basically be moved back inside in order to preserve your coherency. So in many algorithms, say pushing to the front, pushing to the pushing to a vector where there is no reallocation, every single time they won't copy objects even if there are no except false move constructables. If there is any reallocation, pushing to the front, pushing to the back, they will use the move constructors, the no except false move constructors. If you push to the middle, it depends. In some cases, a rollback will be possible, but basically they have this rollback mechanism, which exists in their code, and it's only compiled in these cases. And it's very slow.
Okay,
but
that answers my questions. Thank you.
Thank you so much. I think it exhausts, let's say, the time slot that we are giving for the first lecture. So if we just could spare a couple of energetic, let's say, movements for our presenters. So Borislav, thank you so much once again.
thank you.